Okay, so we were just talking about the Kirby-Bauer technique, right? So this was a way that we could kind of demonstrate if a particular microorganism was resistant or susceptible to a antibiotic or an antimicrobial, right? So pros and cons for Kirby-Bauer, right? So the pros are that this is a really easy method to use, right? Doesn't take much. Anybody can do this type of test, right? You streak it, you throw down the discs, and then you see what happens afterwards after you incubate it. So it's also highly reproducible, right? So you can keep on culturing your bacteria and kind of get the same results over and over again. And in vitro matches in vivo. So that basically means that what you see happening on the plate is kind of what happens in the body. All right. Of course, not considering the intermediate responses, which the intermediate you would not prescribe anyway. So in vitro, meaning kind of on the plate, if you see susceptibility there, then most likely it's going to work in the body. The cons, Kirby-Bauer cannot be used for anaerobes. Typically, you're growing anaerobes in a broth, and they're not going to grow well on a solid medium. So that's not going to work. Also, if you have organisms that are very slow growers, you're not going to get the results that you need in the time that you need it to prescribe something for the individual. And then you could also have microorganisms that are very fastidious. So they just don't like the growing conditions that they're being subjected to, and you may not see the growth that you need to see a zone of inhibition. So it's also very qualitative versus quantitative. So we're not necessarily getting numbers per se, a lot of data, even though we are kind of using a table and measuring the distance, but it's up to everybody who is doing the measuring, right? So where I might say, well, that zone ends here, somebody else might think the zone is extended a little bit further. So there could be differences in how one person measures the zone of inhibition versus another person. So they might say, you know, this is 10 millimeters. Another person might say it's 11 millimeters. So a little bit more qualitative in how each individual interprets that zone, because a lot of times it's a little fuzzy around the outer ring there, and trying to interpret where it actually ends. So we also mentioned there's the tube dilution test. So as it says, this is more sensitive and quantitative than the Kirby-Bauer. So it says the antimicrobial that is being evaluated is diluted serially in a broth. So we're using a broth instead. And I'll show you what this looks like in the next image. So what we do is we take several tubes and we set them up and we inoculate them with our culture and we incubate them. And we're subjecting them to different concentrations of the antimicrobial. And we're seeing which one is the most effective, which concentration is the most effective. And we can look at what is called the minimum inhibitory concentration. So this is the smallest concentration of that drug that inhibits the growth. And that's what we want to look for. Is we don't want to use a strong concentration if we don't need to of the drug. All right, so looking at this, we've got our test tubes in the image above. The first one is a control. So we have the bacteria that's being cultured in this broth, but we're not placing any antibiotic at all in this tube. We just want to make sure that we're able to culture the microorganism. Then the rest of these tubes have different concentrations of the drug that we're testing. So here it shows 0.2 micrograms per milliliter, and then we're kind of doubling it with every tube all the way up to 12.8 micrograms per microliter. And we're looking for the growth of the microorganisms within each of these tubes. So you can see the little white specks representing kind of the growth. We said in broths, a lot of times you're looking for that turbidity. You're looking for it to look cloudy in color if the bacteria is growing. And then if there is no growth, then it should be very clear, like the broth is normally a very clear looking. You can kind of see through it very easily. So as we mentioned in the earlier chapters, you can measure turbidity using a spectrophotometer, and that will give you a value. So the spectrophotometer is going to tell you, and it's going to give you a number. And that's why we say this is a lot more quantitative than qualitative. Down here, we're kind of doing the same type of test. We've got a positive growth control that's showing us pink here. So these are little wells that have been set up, and we see that growth of the bacteria is going to be pink. Then for this row here, we're using a certain antimicrobial, and we're looking at the different concentrations in each one of these wells. So typically you're going from lowest concentration up to higher concentrations as you go along that row there. So you can see the growth, it's pink, it's pink, it's pink, it's pink, and then all of a sudden it turns purple. So this is the minimum concentration here that is effective against this microorganism. And then the next row, we have a different antimicrobial, and we can see it's kind of growing, the growth, it's not halted at all until we finally get to the highest concentration that has been tested. But this would be our minimum inhibitory concentration here, right? Because this is the first concentration that has an effect on the growth of that microorganism, right? So you can kind of see where the X is where we got the color change, and that's showing us the minimum inhibitory concentration. Now, there is what's called an E-test. So that was our tube dilution test where we get the concentration, but you can also get a concentration on a Mueller-Hinton plate with our Kirby-Bauer by using a strip of paper. And these strips have different concentrations of an antimicrobial that have been kind of placed on that paper strip. So it's just like these filter paper discs that we have here that have the E for erythromycin, TE for tetracycline, different antimicrobials that have been impregnated into those antibiotic discs, and we see our zone of inhibition, but this is only one concentration. So to determine our minimum inhibitory concentration, we would need something like this E-test here with these different concentrations of erythromycin. So we see that there's a zone of inhibition here. Now, what's our minimum inhibitory concentration? So you can see as we go up that the width of our zone of inhibition increases, right, until we get down and down and it starts to narrow. And so around 0.25 is kind of where we start to see, and maybe on this side you can see a little bit more. And once again, this is kind of why it's qualitative, because you're kind of making a judgment call of where your minimum is right here. All right, is it at 0.25 or does it go down to 0.19 even? It's very hard to tell in this image, but it's giving us a range here where we can start looking at what's the minimum amount of this antimicrobial that we can use. All right, so given this information, we want to look at how safe is the drug to use. So one measure of a drug's general safety is what's called its therapeutic index. So this is the ratio of the maximum amount of drug that's tolerated by an individual, that's tolerated by the body. So it's basically what is the safe dose that is also effective, right? So it's kind of the minimum amount of the antimicrobial that is safe to use within the body. So in general, if you have a drug with a very high therapeutic index, it's considered to be safer than a drug with a narrow or very small therapeutic index. And this is because a drug with a high therapeutic index would be effective well below the dose at which it is potentially toxic. All right, so we want a large number for this. In contrast, if you have a drug with a narrow therapeutic index or very small, you have a therapeutic dose that is basically close to the toxic dose. And that can be, kind of pretty harrowing, right? So you've got to carefully monitor the dosage and monitor the individual for any toxic side effects from that drug. So here we see 1.1 is a risky choice, and a TI, meaning our therapeutic index, of a 10 is a much safer choice. All right, so we said the higher the therapeutic index, the safer the drug is. We don't want to get close at all to where it's a toxic dose. So here's a question for you, all right, to consider what we've been talking about. So it says, which of the following antibiotics would be the safest choice for a patient with no exceptional medical history? So we have drug A, we have zone of inhibition of 30 millimeters, and we have drug B with a zone of inhibition of 20 millimeters. So the larger the zone of inhibition, right, probably the more likely it is that drug, that microorganism is going to be susceptible to that drug. So drug A with the 30 millimeters looks really good because it's got the much wider zone of inhibition. If we look at the therapeutic index, which is the TI right there, drug A has 1.2, drug B has a therapeutic index of 12. So 12 is the higher number, which we said is the safer choice. So we want a high therapeutic index. So for this, we want to choose drug B because we want to go on the safe side, and we don't necessarily know if that 20 millimeters, I didn't give you a table or anything like that. It could be that 20 millimeters is perfectly a number that would be a number that we would deem to be within the susceptible range for that microorganism. Okay, so we're going to always go on the safe side with the therapeutic index. All right, so we said we need to identify the microorganism. We need to determine its susceptibility to the drug. We've now determined kind of what's the safe dosage. And we also need to take into consideration the condition of the patient. So, as it says, you have to take a careful history of the individual. Kind of what is their background? That's what we mean by their history. So, we need to know what are their pre-existing conditions, right? Do they have asthma? Do they have a heart condition? So we need to look at any allergies. How well does their kidneys and their liver function, since we're giving them antibiotics, and these are basically drugs that your body's going to recognize as a drug and want to eliminate from the body. So how well are they functioning? We don't want to give them anything that would cause even more damage to their kidneys or their liver. Their age, are they pregnant? Are there any possible drug interactions with the medicines that they're currently taking? And what's the easiest way for this patient to take the medicine? All right. Are they able to swallow the drugs? So all these need to be taken into consideration when we're looking at what is the best option for treating an infection.